before talking about MS series, Topology of Foliation, an Introduction by Ichiro Tamura. And this is a book on foliations by Ichiro Tamura, published in 1976. I was just entered in the graduate school in master course. So Ichiro Tamura is my thesis advisor, in fact. And in his book, this is the first encounter with Paul. It was virtual. And as you see, these figures and some others. So you may, if you have a very good eye, here is written Schweitzer. And this explains his construction of the famous dynamical system of the Paul Schweitzer. And this figure is the same figure, almost the same figure, as the Paul's paper in 1974. It is just something like 1 or 2 years after the appearance of Paul's paper, and Tamura was really wanted to make a kind of school on foliations in Japan. So I was just influenced by that. And then the second and first real encounter with Paul was 1982, I think, at Aarhus. There was the Aarhus Algebraic Topology Conference, and it was usually the planned connected to the ICM. But at that year, the ICM was postponed 1 year after. But this Aarhus conference was held. And here is the list of lectures. And you can see here and here. And I have some zoom up. So fortunately, my name begins T, and Paul Schweitzer begins S. So in the list, we are rather near. And at that time, he talked about compact leaves of foliations, and I talked about the second homology of groups of diffeomorphisms. And in fact, I was very happy to talk with him. I think we talked also on the beach near Aarhus. That year, somehow it was very hot very warm in summer. And we talked a lot, I think. And it was just only 40 years ago, I should say, before you. But at that time, I was only 28, and I think Paul was 45. And how do you say? Estamos jóvenes. And then 7 years later, in 1989, I visited for the first time PUC-Rio, your place. And Brazil was in the inflation era. And in fact, Paul and Los Matemáticos Cariocas helped me a lot. And my stay was really fantastic. So, muito, muito obrigado. So, I'm going to talk about sections for flows. And a coordination one, submanifold transverse to a flow is a called section for the flow. I think Poincaré might be one of the pioneers to take a section to a flow and look at the first return map. I think in some sense Paul's flow as well as other constructions comes from the idea of using sections or fast sections or plug-in constructions to modify the given flow. And in a paper in 1917, Birkhoff introduced a surface of section for a flow of three manifold, whose interior is transverse to the flow and whose boundary consists of closed orbits. And this surface is usually called the Birkhoff section. It is used, for example, to investigate anosov flow. And I didn't, sorry, This is a kind of figure not well represented, but if you have a closed orbit like this, and you want to find a surface with boundary closed orbits, and for this surface, the flow is transverse. And for example, near the closed orbit, it should be transverse and come again and transverse intersections and so on. And for example, in the case of anosov flows, from time to time, you can find such section. And if you have such a section, and you can look at the first return map. And then, for example, you will see the surface and the first return map. And at that time, the boundary is a closed orbit, but it will be maybe better to identify this closed orbit to one point and look at first return map of this closed manifold. And this construction tells a lot on the anosol flows. And then, but today I'm going to talk about something real analytic Barkov sections. And in fact, for the very simple flow given by U1 action, the circle action. So this dynamically, the flow is really simple, but I want you to study the group of real analytic diffeomorphisms, and this Barkov section, in fact, appeared rather naturally. And what I want to tell you today is something like this. So we think about close-connected manifold with real analytic, maybe semi-free U1 action. And then real analytic Barkov section is a codimension 1 submanifold, and it is a kind of union of -1 invariant component. And if you have such Barkov section for U1 action, we can construct a U1 equivalent map from the manifold to a complex plane. And then we can define orbit-wise SL2R action, and this will imply the perfectness of the group of diffeomorphisms, group of real analytic diffeomorphisms, which are isotopic to the identity. And here, more or less, I want to explain what happened in my investigation of the real analytic diffeomorphisms. Okay.
Takashi?
Yes?
Can I ask you, what does it mean -1 invariant components?
I'll tell you.
Okay.
It's fine. Not the end. It comes. So, in fact, I can tell you in some reverse direction. So usual notation, let diff omega of M denote the group of real analytic diffeomorphisms of a closed real analytic manifold M. And with 0 here, diff omega of M0 denote the identity component with respect to the C1 topology. So what was striking result? Now, it is something almost half century ago that a group of diffeomorphism, real analytic diffeomorphism of n-dimensional torus, which are isotopic to the identity, this group is a simple group. Simple group means there are only two normal subgroups one is the group itself, and the other is the identity. Just one element group. And then much later, but already more than 10 years ago, I could show that if manifold admits free U1 action, this means the manifold itself is a U1 principal bundle over n-1 manifold, or special semi-free U1 action. That means this manifold is obtained from the n-1 manifold times U1, and just identify the boundary of n cross U1 to the boundary of n. That is just crashing out this U1. And then if this manifold admits such a good action, then this group is a perfect group. For these groups, perfect, simple means perfect, but for the group of real analytic diffeomorphism, we don't know whether the perfect implies simple. And also, I could show that for the low dimension 2 and 3, if the manifold admits non-trivial U1 action, then this group is also perfect. So in fact, Ehrman conjectured that for these groups, for any manifold, the analytic diffeomorphism group is a simple group. But I have rather modest conjecture that if this group manifold admits non-trivial circle action, then this group is a perfect group. And we have some more evidence. That means CP2 or CPN has circle actions. And a group of diffeomorphisms of real analytic diffeomorphism isotopic to the identity is perfect. We can use this U1 action, and we can show that the diffeomorphism group of them are perfect. And also, if the manifold has same-free, I'll tell you later, and U1 actions, and fixed point is the something simpler type acting on this, then also the group is perfect. The reason that I'm looking at such a manifold is the following proposition I showed. That is, if the manifold admits non-trivial U1 actions, then any element of a group of diffeomorphism is homologous to an orbit-wise rotation. so there is circle orbits, and each orbit turned by some rotation. And so if we use this proposition, it is only necessary to show that orbit-wise rotations are written as a product of commutators, then that's it. So in order to write some element as product of commutators, I think we may use the diffeomorphism mapping orbit to orbit, or the diffeomorphism mapping each orbit to itself. And for the moment, we use the diffeomorphism mapping each orbit to itself. Okay. The reason is that the rotations are written as the product of commutators in SL2R, or its finite coverings, in fact. But anyway, in SL2R, it can be written as a product of commutators, and it is also written in some, if this orbit-wise rotation, the rotation number changes real analytically, orbits by orbit, but we can make them as a real analytic family of elements of SL2R. For example, in this way. So this is something like the square of the rotation, and this can be written as two commutators, and this matrix is written like this. So if we can define a nice orbit-wise SL2R action so that this element and A depend on the orbits, act really analytically, then we can use this to write orbit-wise rotation as a product of commutators. And from time to time, it will be necessary to put this matrix to be identity at some orbit in M. So, but we can still write an orbit-wise rotation as a product of commutators if the rotation angle, this is this Y, is divisible by A minus 1. So in the real analytic world, you can think about the division. And then if you look at this expression, if this Y can be divided by A minus 1, and then A is some number near 1. So this expression becomes real analytic. Okay. So this figure shows the so you can think of the set of circle as a set of rays, And then this is just circle. And hyperbolic element will make the contraction to the x-axis or contraction to the y-axis. So the diagonal matrix acts like this. And it is, in fact, I think some calculation become easier if we use complex coordinates for the usual xy coordinate. For this, we can write the action of this matrix on this complex number to be a times x and y over a for y. And then, so this is just, I write az over the absolute value of az. So if we look at the concentric circles in C, and the action is something like here, the action to the angle, and then here, the absolute value of Z. And then this can be written like this. And this expression can be calculated this way. And we see here that if the square of the absolute value of Z divides a minus 1, then this A acts real analytically on the concentric circles in C. The figure is something like this. So the action is almost identical in the center, and this is hyperbolic, more than more hyperbolic in the exterior. So something like this. And in order to make on the circle, it is necessary that the action should be identity at the origin. So, and okay, this is some not very big thing, but we restrict ourselves to the case of semi-free U1 actions. And semi-free U1 actions means orbit other than the fixed points are free orbit. And locally around the fixed point, the structure is determined rather easily. And for a fixed point of the semi-free U1 action, there is some k positive integer, and you can take a coordinate like c to the k and r to the n minus 2k, and the action is just rotation for this C coordinate. The good example is CPN, and it admits a semi-free U1 action, and in the homogeneous coordinate, this U act on the first k+1 coordinates. And then the fixed point set is, in this case, this part is Cpn minus k minus 1. And this can be sent to U minus U inverse here and there. So this part is also fixed point and Cpk there. And action we are looking at is something like that. So, well, what comes to us is the following thing. And what I told you, we can make act on the concentric circles. And usual Barkov section, if we take, should be the Lie. But if we want to define the real analytic set, that should be using some real analytic function or map, and it's the zeros of this real analytic function. So this Lie itself is not real analytic, and you have to put the Lie of the other direction, and you have to have the line x-axis, and it should be -1. There is -1 action in this U1 action, and this part is -1 times the positive Lie. Okay? And then, so the analytic Barkov section we want to find is, I think it should be some real analytic set. Then we should think of something like the double of usual Barkov section. And there we have -1 action of this U1 action. And we are thinking the actions with fixed point, and these fixed points should be in this section. And there are also another set, which is a union of non-trivial U1 orbits. And it is written here that it is a section. I mean, the surface minus these fixed points and union of orbits is transverse to U1 orbit. So this is what I mean -1 invariant. And we want to assume that this surface, hypersurface, is given by a real analytic function And then this real analytic function should be an odd function, meaning by the -1. So here you have some point P and U1 action. So you have -1. And then you look at this F equals to minus F P. Okay. So, but it looks rather strange because the F should change sign on U1 orbit. And in fact, orbit hits S twice transversely. So that is for the concentric circles, it's the x-axis or any line passing through the origin. So here are the two easy examples. One is just the rotating sphere. U1 acts these are the U1 orbit, and North Pole and South Pole are the fixed point, and the fixed point set is North and South Pole. And for example, the function can be written as the y coordinate, and then the S is the gray circle, and every orbit hits twice. And the back of section in usual sense is the half of that. And then if you look at, you have action by I, the square root of -1. Then this will, so this is, I should write H of P equal F of I P plus I times FP. And this is a complex valued function. And this is in fact U1 equivalent. That means just you see on this figure, if you turn around something, then in fact the mapping is the projection to the XY axis. And if you turn along the orbit, and that will give you the image will be turned on the concentric circle. And the other example is the Hopf fibrillation, and that is U1 acts on S3 diagonally. And then S in this case is some hyperplane, and this is given, for example, the imaginary part of Z2, and Z here is a circle given by Z2 equal to 0. This is in the Hopf fibrillation, you have to have dual of the Euler class of this fibrillation, and this is represented by this circle, or in fact, the point on the CP1, and in S3, it's a circle. And then this H is yeah. No, I can't. Well, how can I make it? Oh, it's not very nice. So, I'm sorry. Yeah, here you can see the figure of the Hopf fibrillation, and then what I'm telling you is you will just take the center of this orbit, one orbit, and then this is Z, and you will take a plane containing this circle, and that is S, okay? And then we can define the function H like this, and this becomes a U1 equivalent. And then this means the U1 orbits in this set are mapped to the concentric circles in C, and S is mapped to the real line. And in fact, F union Z is mapped to 0. And as I showed on the concentric circles, we can define the SL2R action, orbitwise SL2R action. So this will induce action on M minus F union Z. And then we can show that if this function divides A, then this action extends real analytically to the union of F and Z. So we can verify for many examples that is for the same free actions, the problem left is to find the good Barkov section. And what I did in my previous work, the free U1 action, and as I told you, Z is the codimension 2 submanifold dual to the Euler class. And for the specially same free U1 actions, just S is the double of N. And for CPN, we can find also. And for some restricted actions, we can also find S. And I think for other safely U1 actions, there are still several things to do. But I hope we can find good Markov section as well, and also for the other U1 actions. So that's all what I want to tell you today. So thank you very much for your attention. Happy birthday to Paul. We are always happy to be with you. Thank you very much.
Thank you, Professor, for your very interesting lecture. Do we have questions?
Mm-hmm.
Yes, I have.
Please.
Takashi.
Do you hear me?
Yes.
So is there any real analytic manifold, maybe without circle action, and whose group of real analytic diffeomorphism, maybe its connected component is not perfect?
I don't know.
I see.
So that's why I told you the conjecture by Ellman. He conjectured it's simple group.
Ah, he conjectured simplicity. I see.
Yes, but I think I don't know how to do that. And then okay. I weakened the conjecture. I hope to show at least perfectness, and I hope to do it for some restricted family of the manifolds.
Okay,
but
I see.
For example, CPN is very nice.
Takashi, could I ask you about
the circle action that you are assuming? I'm sorry.
Go ahead.
Yes.
The circle action you are assuming is that it's real analytic action.
Yes, yes. It should be real analytic action.
If you don't assume, then can you modify it into always real analytic? If the action is not known to be real analytic, can we modify?
That's a very interesting question. I don't know.
I see.
There are many, I think, not many, but I think there are some example which is not a linear action. And the construction looks somehow differentiable, but I don't know whether it is real analytic or not. Maybe. Yeah.
Takashi, could I ask
yes?
whether with all of the work that you have done on this problem, have you any kind of feeling about what should be the case with Hermann's conjecture?
Oh, I don't know. But up to now, we are very far from the solution. And if I could show for this manifold with circle actions, and the next target should be the solved manifold, the torus torus fibrillation over the circle was such that. And then some other, yeah, the surface of genus 2 is the very difficult target, I think.
So thank you. I would like to just mention, Takashi, another moment when we met. It was also in 1982 at the Institut des Hautes Études Scientifiques, the IHES.
Yes,
we were
yes.
both there. And I was hoping to go to the Leningrad International Topology Conference
That's right.
right after Aarhus. But I had applied for a visa to the Soviet Union and had made no
Yes.
progress at all. But at the IHES, many of the professors had contacts in Russia, and they said, oh, you shouldn't try to get a visa to go to the conference. You should just find a group of tourists that is going to be in Leningrad for that week and get on that group. And
Right.
so I was very discouraged at that time. But you encouraged me, and you took me into Paris, and we went to an agency for the travel to the Soviet Union for tourists. And you helped me find a tourist group, so I did get to go there after all. So thank you for that.
I thought to mention that thing because I think you met Tamura there.
Met who?
Ichiro Tamura.
I think so too. Yes, I think so. That was
Yeah.
right.
I knew of that conference because of Tamura. Tamura wrote me that he will attend that conference. So this is also one of the reasons I recommended you, or I went with you to the to our office. Yes, right.
Okay, thank you. Are there any more questions? No? So let's thank the speaker again.
Thank you very much.
So now we have a short coffee break, and we come back in what, 5 minutes? 10 minutes. We come back in 10 minutes, okay?